Okay, so stoichiometry review, or sorry, stoichiometry summary. Now on your page, you'll notice that there's a whole bunch of, like this big map that has all these different conversion factors on there. And normally I build that with you. What I'm going to do a little differently, and this isn't really a big deal. It's still writing the same stuff down. You don't have to write this down if you don't want to, but you can put it on the back. I am just going to use a page on Smart Notebook here, and I just want to make a list of all of the possible conversions that we've done, all right? Now, it is in that map that we've done, but I want to just present it in a slightly different way so that we think about it a little differently. So essentially what I'm going to be writing down here is a list of the conversions, all right? Conversions or conversion factors. Let's just put conversions, different conversions that we've dealt with, all right? And I'm just going to make a list of them. The first one we dealt with, I believe, was mass, right, to moles. And if I want to convert mass to moles, oh, that's so sad. Molar mass, thank you very much. Molar mass, all right? Now, I guess I'm going to make a little table here. I guess the question I want to ask is, where do we find this, or where do we get this? So maybe at the top here, so the conversions, and then I'll put here, right, where to find, all right? So I guess I'm making an unofficial table here. And then sometimes there's an equation that goes with it. So let's just put here the equation that you could use instead. Now, some of us have been using equations, but most of us have been using conversion factors. So where do I find the molar mass? Periodic table, excellent. Periodic table. And I also need one other important piece of information. Not just the periodic table alone will get us the molar mass. I need to know something else in order to get the molar mass. What do I have to have? Yep. The chemical formula for that substance. So the periodic table and the formula. All right? Now, in a question that we dealt with not very long ago, just a couple of days ago, we were actually asked to find the molar mass. And if I'm asked to find the molar mass, not from the chemical formula, but from some data, what's the data that I need? Now, the neat trick for all of these things is that you can always generate an equation if you know the units of the thing you want to find. I guess the question is, what are the units for molar mass? When you get molar mass, the thing I tried to instruct you was to always write down this unit, and I also wanted you to think it so that when you had to think it, you could figure out what's the unit. Grams per mole, which means if I want to get the molar mass, what do I have to put on the top? Grams. And what do I have to put on the bottom? Moles. All right. And you know what? That's not a typical equation because it doesn't have variables in it. It's got the actual unit. But you know what? When I got about into second year university, I realized, why am I memorizing all of these equations when the equation is really built into the unit for these easy guys? So if I know the grams and I know the moles, then I can figure out the molar mass if I need to get that. All right? Okay. So the next conversion factor we encountered. The next one we encountered was when we first started to do stoichiometry, and we wanted to convert moles of substance A into moles of substance B. And when I say converting it into it, I wanted to figure out how much I needed or how much I was going to produce. What am I talking about here? Does anybody know which one I'm talking about? Yeah, the mole ratio. Excellent. Mole ratio. Where do I get the mole ratio? Yep. Yeah, it comes from the BCE, and that's my little short form for balanced chemical equation. You've seen it on tests. If you haven't balanced it correctly, it'll say BCE question mark, that kind of thing. All right? Now, there really is no equation for it. I guess what I've been telling you is what we have you put on the bottom, and what you want to convert it into you put on the top. I don't think there's really any way to put that. I guess we could say number that you have on the bottom and the number that you want it to become on the top, right? I don't know. We haven't really talked about an equation for that. And that number, right, is that coefficient. That's that number in the balanced chemical equation. All right, excellent. 3. The next thing we encountered was were solutions, right? Where we may have had a volume, and now I've got to be careful. I got to put here volumes of volume of solution, because instead of volume of gas. And if I want it to become moles, what was the conversion factor called for that conversion? Convert volume of a solution into moles. I needed to use this. Yep. Yeah, now that's the equation. I'm going to put it right over here. C equals N over V. Excellent. And that's the concentration. And another way of writing the unit for concentration, remember, was capital M, the molarity. And molarity will always be in moles per liter. That's another way of getting the equation. Molarity's units is moles per liter. And then we got to flip it around and do all this stuff, right? And where do I find the molarity for a question? If I'm doing a question and you need the molarity, where would you find it? Can you get it from the periodic table? No. So where did the molarity have to be? Yeah, Jason? It's in the question. It has to be given. So in other words, they've got to tell you what it is. So in this case, it must be given. And that's because any solution can really have any concentration depending on the scientist who made the solution. All right? Now, I've already mentioned that it really can't have any. You can't have like an infinite number for moles per liter. There will be a maximum where it then can't dissolve anymore. But really, anything between that maximum and 0, right, can exist, a concentration value. So it must be given, all right? So it's dependent on the solution. Let's put here, depends on, and it really depends on who made the solution, on who made the solution. And we've all encountered questions where we have to find that conversion factor, like a titration problem where it asks what is the concentration of, and you've got to figure out the N, and in the question they'll give you the V, and then you use C equals N over V. Okay? All right. And that brings us now to gases, number 4. Volume of a gas. And I'm going to put here one little bit of information, at STP or SATP. And if I want to go from the volume of a gas at STP or SATP and convert it into moles, well, I'm hoping this is fresh in our minds. Yesterday fresh. What conversion factor converts volume of a gas to moles if it's at those special temperature and pressures? Molar volume. MV, molar volume. All right? Well, where would I find the molar volume? No, it's not in the question. They'd have to say STP or SATP, but once they've said that, where would I find that? Yep. It's on your sheet. It's on the equation sheet. And why can I just go straight to the equation sheet? Why do I not need to worry about the chemical formula, or why do I not need to worry about who produced the gas? Why is it different than the molar mass and molarity? what's true about gases? Yeah? Yeah, they all behave the same. Doesn't matter what the identity is. So it's on the table, but essentially, you don't even need to think about it. I'm going to just put here molar volume, STP. Well, what is it? I don't have it memorized. Now that I've put it on the sheet, I used to memorize it, but now that it's on the sheet, just go tell me what it is. Yep. Sorry? 22.4? 22.4. And what are the units? Liters per mole. All right? And MV at SATP, what's it? Yep. 24.8 liters per mole. All right? I guess if I were to make you find a molar volume, I guess I could do that. And you would get the answer of 22.4 or 24.8. But if I asked you to find a molar volume, what would you need to do? What two pieces of information about the gas would you need? Think about the units. It's all in the units. Yep. Yeah, and how would they go in my equation? I would need volume in liters on the top, and I'd need the number of moles on the bottom. And if I took any gas, and it was at STP, and I somehow collected it and measured the volume, and I collected it and I could mathematically figure out the moles, I could put that in there and I could figure out the molar volume. I should get the number that I'm expecting, but I could easily do that. Just like we figured out molar mass. All I would need is those two pieces of information. Okay? All right. And I'm going to move down because we've really got one more situation that we've got to deal with. We'll extend the page a little bit. So number five. And that is volume of a gas. All right, gas. I don't know why I put that extra letter there. 2 S's on gas for today. And this is not STP/SATP. And I need to figure out moles. And if it's not at STP or at SATP, then what equation do I have to use? Yep. Yeah, I've got to use PV equals nRT. And if I'm given the volume and I want to find moles, in other words, I want to find N, then I'm going to need the equation with the N on its own. In other words, I'd solve for N. And if I was going back the other way, I would then be solving for V. All right, we'll do examples of this. So we solve for N if we're heading one way, and we solve for V if we're heading the other way. Again, where do I find it? It's true for all gases, so it's not a big deal. True for all gases. And really, there's nothing for me to calculate here. We already know the equation is PV equals nRT, so I could calculate all kinds of interesting things depending on what I need. Okay? So those are all of the tools that we can use when doing a stoichiometry problem. We just need to look at what we're starting with, where we want to go, and then where we want to end with. All right? We just need to pick the appropriate equations and the appropriate numbers. Okay, let's head back to the PowerPoint. And this next little summary slide is the whole thing on here. I used to do it this way, blah, 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 blah. And that's not a big deal. Oops, let's back up to 1. That's not a big deal. We essentially covered this. But let's say I have mass of A and I want to figure out a solution of B. Then I'd use the molar mass of A, mole ratio. I'd use the molarity. Maybe I want to figure out what volume is needed. And I can figure out volume of B. So this kind of map just tells you where you would go. Let's say I started with a volume of hydrochloric acid, and I want to figure out the volume of the gas that's not at SATP. I'd use molarity, right? The volume of the solution. Figure out the moles of B. Then I would take the moles and substitute it into N, and I'd figure out V using PV equals nRT. So I'm just doing those 3 steps always. So with all stoichiometry problems, there's a step 1 where we move down. You got to pick the appropriate equation or conversion factor. There's a step 2 where we move across. That's our mole ratio. And then there's a step 3 where we move back up and we figure out what we want to find, and we just pick the appropriate equations depending on what they're asking. Keep in mind, yesterday we learned about the law of combining volumes. If I'm starting with a volume of a gas and I'm looking for a volume of a gas and they're at the same temperature and pressures, then I take a shortcut. I just use the mole ratio. Okay, examples. Now all of my that first example that you have on yours, there's been a couple of times where I haven't had enough time to do the law of combining volumes by itself. So I stick that example on my page. We did that example yesterday where it says shortcut law of combining volumes. We did that one yesterday. So now I've moved on to the next one. Everybody find the question that we're on now? Everybody tracked it down? So we did the law of combining volumes yesterday where it says shortcut, right? That's yesterday. So now we're working on this one. All of my examples, all of my questions on test/exam will not be determine the equation. All of my examples here, I need you to determine the equation. I want you to practice it. There's a mix on the exam and the test. Some I give you the equation, some I don't. That deal that I've been giving you all the way along, if you're completely spinning your wheels and you don't know the equation, I'll give it to you, but you'll lose those marks that you would have got for doing the balanced chemical equation. So let's work together on this one. 200 grams of sodium chloride dissolved by decomposed by hydrolysis. Decomposed by hydrolysis. So, reactant. What am I starting with? Oh, knock on the door. That's fine. Hello. Yep.
Amy home in here.
I do. Amy? Yep.
Talk to her for a couple seconds.
Yep. So, what's the reactant here? What are we starting with? Yep. Oh, thanks a lot. I was feeling a little concerned. We've gone through an entire course on chemistry. We've done all different types of reactions, and we're spinning our wheels on sodium chloride. It's being decomposed. What are the products? Jenna, what do you got? Plus Cl2. Excellent. We need to balance it. 2 Cl's, 2 NAs, 2. I'm starting with 200 grams of sodium chloride. 200 grams. And in A, we want the mass of sodium chloride, sodium obtained, the solid. And in B, what's the volume of the gas obtained at STP? So let's do A here, where we're going to do this. Now, really, I'm just writing here, but I'm hoping you're all writing this stuff down without even thinking, because this is what we've been doing, right? So I'm pretty sure we've got to go to moles. For part A, we're going to find moles. Here at the top, I'm doing question mark grams. I'm hoping at this point you're going for the periodic table, because I need a bunch of molar masses, and we're doing the question, right? Because to go from gram to moles, molar mass, mole ratio, molar mass. Let's assume that the 200 grams is 3 significant digits, that it's exactly 200 grams. Hard to tell with the way it's written, but we'll assume that. And we're pros at this point. What I mean by that is you don't have to write 200 grams of NaCl, right? We know it's NaCl. We know we need the molar mass of NaCl. Same with the mole ratio. At the very beginning, when I taught you this, we wrote down 2 NaCl. We know that. What we have, we put on the bottom. What we want, we put on the top. Now I need the molar mass of Na. I'll take an answer. Yep, Amy? Oh, she wasn't ready. Carissa, what do you got there? Grams. Na. You can put that, but not a big deal. You don't have to. 3 significant digits. Excellent. If this was a test, I asked you to put a box around it so my eyes can be drawn to it. Makes it easier for me to do the marking. Part B. What volume of chlorine gas is obtained at STP? So in other words, we can go straight across with our mole ratio. Moles. We want volume, gas. Again, no need to write that brackets gas in there if you know it. You've read it. What's the conversion factor I need? Because I like to gather up all the conversion factors before I get going. I want to find the volume of the gas. I need to go from moles to volume of a gas at STP. Yep. 22.4 liters per 1 mole. Excellent. That's the molar volume, right? At STP. 22.4 liters per 1 mole. That's the molar volume if you were to write in just MV. So now we start again and run on through. Still starting with our 200 grams of sodium, which means the first part looks exactly the same. What we have on the bottom, coefficient of what we want on the top. Now, I need to get rid of these moles. I need mole on the bottom, and I want an answer that is volume. So I need the volume on the top, 22.4 liters per 1 mole. That cancels everything away. Volume to 3 significant digits. Jenna, what do you got? 38.3 liters of Cl2 gas would be collected. So nothing earth-shattering here. Same old stuff, except now if we're talking about the volume of a gas, we may need to use a molar volume. Or PV equals nRT. We'll have one of those later on. Okay? Again, if I'm doing this on a test, I put square around it. You don't have to do that in your notes. It's up to you. Okay? Let's do the next one. Again, no need to wait for me to lead the way. They're just regular stoichiometry problems. In this case, we are going to need to use a PV equals nRT and do a little extra calculation on the side, but that's okay. We can still set everything up. What mass of magnesium metal is needed to produce 250 milliliters of hydrogen gas at 20 degrees Celsius and 750 torr when reacted with 0.5 molar hydrochloric acid? Let's worry about the balanced chemical equation first. What are the reactants in this one? Pause for thinking. Thinking is happening. I see some people rubbing chins. That's an indicator of thinking. Scratching heads. Chewing on pen. It's another thinking indicator. What do you got? Mg plus HCl. Mg plus H. Oops. Let's put an H in front of that. Oh, which means my coefficient's going to be really screwed up. I don't know if I need a coefficient, but I better back that up. Okay. Plus HCl. What are we producing? Yeah, Jenna? H2 plus MgCl2. Didn't leave enough room there, but that's correct. That's very good. And cross over the 2. H2 is Hofbrinkel. Excellent. Now we need to balance. It's looking like I just need a 2 there. Let's put our information down. What mass of magnesium metal is needed? Question mark grams is what we're looking for. We are producing 250 milliliters of hydrogen gas. So 250 milliliters. And it says here that it's at 20 degrees Celsius and 750 torr. And that is definitely not STP or SATP. Which means, what do we have to use to go from my milliliters down to moles? How am I going to convert that volume of a gas to moles if it's not at those nice pressure and temperatures? Yep. I have to use PV equals nRT. So in the end, I'm going to need to use PV equals nRT. Now, what I like to do when I get a stoichiometry problem that isn't at STP, on the arrow, I like to put the T and I like to put the P. All right, because they're going to have to give you a T and a P in order to do the equation. Here's the V. You'll need a T and a P, and you'll solve for N. Now, right in that, and I know it's tiny writing for all you big writers, for all you big fat writers in the world, and I'm one of those people. It's kind of a pain, but I like to put the T 20 degrees Celsius, and we already know what has to happen to that degree Celsius, which means right in there I'm going to put a little equal sign. And if you're doing this on your little page, it's probably the tiniest little tiny writing, you squeezing it in that little square. Oh, it's entertaining. You need a sharp pencil. 0.5 milliliter lead. What is 20 degrees Celsius? What do I need to turn that into? We're dealing with gases. It's got to be turned into this. Kelvin. So what is it? What do I have to add to that? 20. All right. That one we can do in our head. What is that? 293 Kelvin. Pressure. This is going to get squishy. 750 torr, which is the same as millimeters of mercury. I need to put a little tiny conversion factor in there. What goes on the top? What goes on the bottom? This is the type of thing that I need as a, you know, as just something that we do. Carissa, what do you got? 101.3 kilopascals. Nope. 760 torr, or millimeters of mercury. So again, we're doing a little quick calculation that I don't want you to consider as a big thing. It's just a quick conversion. We just do it, you know, just do it. Something that we just do without having to stress over it. And what do we get for a number? Yeah, Jenna? 100? 100? 100? So 100 to 3 significant digits, kilopascals. Okay. And then we're going to go over here to moles when we get that all done. And then we're going to move up here to mass, and we know that we just need a molar mass to do that. And of course, we need the mole ratio. So now the first step is different. The first step, we need PV equals nRT. And we are going to solve for moles. We know the P, 100. We know the V. Got to be careful on this. We have got to put in liters. Actually, if you didn't put in liters, you'd end up again with millimoles, right? If you had milliliters, you're going to end up with a unit of millimoles again. We better keep it just in moles because we're not going to be using a solution. But if you left milliliters, you end up with millimoles, just like we did with solutions. So we better put in our 0.250. We're looking for N. I just write that in like that. Anybody remember the R? 8.314. Isn't it scary when useless numbers are in your brain from just learning it? I think it's cool. All right. we did that, T293. Again, like I said, we know we're going to divide these off. So I don't need to see an extra line of writing. You can put 100 times 0.25 divided by 8.314 divided by 293. You don't need to rewrite. What do we get? How many moles? Jenna is looking at a number. What do you got? 103 to 3 significant digits. That's nice. Moles. Now we are right here in our map. Now I'm going to just write those moles down, and I'll just keep doing my conversion factors that I normally do. 0.0103 moles of H2. Now my map tells me I need the mole ratio. What I have on the bottom, 1. What I want it to become on the top, 1. And now I need a molar mass of magnesium, and I need to have grams come out at the top. And what is that molar mass? Paisley's looking at it right now. 24.3 grams per 1 mole. And then you complete it. Jenna, what do you got? We want one more significant digit. 250? Excellent. Thank you. 250, and that is grams. Grams of mg. Grams of mg. Okay? All right? Every stoichiometry question that doesn't like start with a moles or end with a moles, but starts with something else that isn't moles, will have these 3 steps to it. And I think many people know this. I've seen many solutions from students in both of our classes, this one and the afternoon one, where many of you like to break it into 3 steps. Let's do the first step, turn it into moles. Let's rewrite a second step and turn it into the other moles with the mole ratio. Let's do now a third step and convert it into grams or whatever. And that's fine. That's a good way of thinking. It means you're really thinking about what each step does. Again, we've completed the 3 steps. Converted into moles. Wasn't the conventional way of doing it, but we did it. Then the mole ratio. Converted into the moles of magnesium. Then the molar mass to get the grams. Okay? For those of you who like to see patterns, some of you who go like really crazy on saying, does this mean we just have to do this? Notice, look at our 250 milliliters, which is 0.25 liters, turned into 0.25 grams. Coincidence. That's not a pattern. It's coincidence. All right? So don't be thinking about patterns. Some people do. They get really excited about patterns. It turns out that the factor that we use here in PV equals nRT is very close to this number right here. Coincidence. All right? Don't be looking at all these special patterns. All right, let's do another one. Oh, I missed part B. That's no fun. Back up. What volume of acid is required? Okay. So part B means that we can go from here to here and then up to this guy, right? We want volume of solution. We need a conversion factor for the hydrochloric acid, 0.500. What are the units when we have molarity? What do I tell you to change that into so that we can get it flipped over properly? Yeah, moles per liter. Moles per liter. I don't need to redo this step. I've already done the step, and I've already got the moles. I already have 0.0103 moles of the H2. All I need to do is now complete the last 2 steps again. Mole ratio, in this case, it's 1 to 2. It's an ugly looking 2. This time, I need to use the concentration. I need liters on the top because I want liters as my answer. So how many liters, and that's a mole on the bottom. How many liters are we expecting? How many liters do we need here? It's not going to be much. Yep. Maybe one more significant digit. Sorry? 1, 2. And I'm not sure. That's going to be liters. Is it? We got supporters on that? Yeah, it won't be very much. Be a tiny little amount. That's 41 milliliters. So about 41 milliliters of that with 0.25 grams of magnesium, I would expect to get 250 milliliters of gas. All right? Okay. Volume of oxygen gas needed to combust 25.3 grams of octane. Combustion reaction. We talked about this yesterday. What are my products of a combustion reaction when we burn a hydrocarbon? A whole year of chemistry. Excellent. How many carbon dioxides will be produced? Yep, 8. It's the same as the carbons. All the carbons here have to end up there. How many waters will be formed? 9. We divide by 2 the number of carbons. How many O2s will I get out of the CO2? 8. And how many O2s can I get out of my H2O? 4.5. 8 plus 4.5? What's that? 12.5. And I have hardly enough room to squeeze that in, but I will, 12.5. Like I've said, if you're doing stoichiometry, leave the 0.5 in there. If it's in the question, please balance the following. Double it all up. Make it look proper. All right? Okay. 25.3 grams. And we want volume of a gas. What are my conversion factors that I need? From beginning to end, just list them off. Some of you have already gone ahead and started calculating. That's excellent. Molar mass, excellent. What else do I need? Mole ratio, good. Molar volume, excellent. And which one is that? Go to your periodic table. If you can read it on the front. You know, they're tiny on the front too, eh? Which one is it? 24.8. Oh, and also the units are very important, but that's also given on the equation sheet. I'm so generous. You're welcome. What is the units for that? Liters per mole. How's it going, Jamie? Does somebody have a molar mass for C8H18 as I was babbling away here? We've already got it. Jenna, what do you got? 114.0 grams per mole. Are you guys already waiting with the answer? That's fabulous if you are. Now you just got to write it down and do all this stuff. 25.3 grams. 114.0 grams per mole. Oops, the mole goes on the top. What am I doing? 1 mole. 1 to 12.5 is the ratio of octane to oxygen. I need a volume out, so I need liters on the top. I need some theme music as you guys are calculating, like a Jeopardy theme of some sort. And I can stop it and say, okay, what's the answer? That'd be fun. I should program that next year. What do we got for an answer? Yep. 8.8 liters of O2 is needed. Okay? What volume of carbon dioxide is produced? Now, normally I would say, all right, this is easy. All we're going to do is go now over here to carbon dioxide and we're going to be done and away we go. But in actual fact, we now know this volume right here. We know this number to be 68.8 liters. And the carbon dioxide is going to be produced also at the same temperature and pressure. We're going to make the assumption because we don't say otherwise, which means I can go like this, straight over there, save a little bit of time, and I can get the volume of the gas, question mark, CO2. And what do I need if I go straight across? One gas to the other gas, same temperature and pressure. What does it? Just the mole ratio, and you've got it. So I can simply go 68.8. Now I'm starting at the oxygen number, so that's 12.5 to 8 is the ratio. And I'm done. So a shortcut is available sometimes. Yep. I would think we should get a volume that is less. You did it backwards. You did the 12 on the top. Amy, what do you got? Sorry? 44.0 liters. I guess this is O2 needed and this is CO2 produced. Not a big deal. I just wanted to put that down, clarify it. Okay? And do I have 4 or 5 examples on this sheet? Just 4? 4? Last one. Exciting. What volume of hydrogen gas at 105.2 kilopascals and 18 degrees Celsius, which means we're going to be needing PV equals nRT, is produced if 2.51 grams of zinc is reacted with 50 milliliters of 1.25 molar sulfuric acid? That doesn't look like fun. Why doesn't this look like fun? That's true, but there's also more evil hidden in this question. Let's get the balanced chemical equation, get our data out there, and then you'll see why this is slightly painful. What are our reactants here? Yep. H2SO4, excellent on the sulfuric acid. Nicely done. We'll keep going. ZnSO4, 2. Excellent. In the end, we're going to get this volume of the gas, and we'll gather up all that data in a moment. I have 2.51 grams of zinc, and I also have 50 milliliters of sulfuric acid. Why is this not so fun? Yep, Jason? Yeah, I don't know which one to use. It's a limiting reagent problem. I got to figure out which one's going to run out and not before I even do the other problem. So, limiting reagent. We know how to do that. We're going to convert over to here to find out what's needed. All I've done here, I put molar mass, and I put here the concentration of the sulfuric acid in moles per liter. Molar mass of zinc, I don't need to write it on the side, but does anybody check that? Anybody have that? 65.4? I've dropped some units here, but again, if you drop some units as you get going, as long as we're doing it right, I'm not concerned. I want units in the answer. I want proper numbers of significant digits in the answer. But if you drop units along the way, I'm not that concerned. Some teachers would be horrified at that statement, but I'm concerned that you get the right answer. And if you get stuck because you're not sure what unit you're going to use, then put units in. Make sure you put them in if you're getting stuck. But if you've got this mastered, go ahead. What do we have for volume of H2SO4 needed? Nathan, you got a number? You're looking at a calculator, but you're not sure. What do you got? 0.03. Anything else? 0.7. Now that's liters, right? And this is milliliters. So we got to switch something over. Why don't we switch this back over to milliliters? Again, I want to put H2SO4, and I want to say needed. I was writing that in capitals earlier on, but now I got it smaller. What is this in milliliters? Yeah, Taylor? 30.7, oops, that's milliliters needed. And remember, I always say, go back to this, and in your head, you can even say it as goofy as I do, I have 50 milliliters. I only need 30. Oh, I have excess. I have plenty. I have too much. Whatever you want to put in there, and therefore, excess. If you do it the other way around, you say, 30, 50, oh, 30 is smaller than 50. It must be limiting. You always end up getting false logic if you don't go back to what you have and compare it to what you need. All right, I've seen examples of that on previous tests. So, limiting reagent. What does that mean? It means we're going to head over to here, to moles, and then I'm going to stop, and then I got to put that in PV equals nRT. All right? So because I don't have it as a nice one, at this point, I'm going to need, and I'll just put this in a different color here, I'm going to need, at that point, PV equals nRT. I'm going to do that at the bottom, but that's what we're going to be doing. So let's gather our information. P, 105.2 kilopascals. Well, no conversion needed there. T, 18 degrees Celsius. Yep, we need to do some changing there. Have we got it? 291? 291 Kelvin. Okay, let's use our conversion factors to get us to here, and we'll stop at moles. 2.51 grams. 1 mole per 65.4 grams. Coefficients, what I have on the bottom, and I'm heading over here, and this is a 1 to 1 to 1, nice and easy, 1. And then I stop. I stop and get an answer of moles. It's actually an answer of moles of H2. Yep, Jenna? 0.03. Oh, we'd like another one after the 8. 384? 383? Okay. That is N. We know the P, we know the T, we know N. We're solving for V. Again, no need to rewrite if you understand the way your calculation works. Times, divided by 105.2. And we'll just finish it off up here. Therefore, volume is. So 0.8. Again, if you didn't clear your calculator, you've got answer times 8.314 times 291 divided by 105.2. Yeah, Jenna, what do you got? 881 liters, and that's of H2 gas. Okay? That's good stuff. That's like putting it all together. But again, every one of these problems has the 3 steps in it. Okay, let's get the moles. All right, let's use the mole ratio to figure out what the next moles is, and then let's use those moles to figure out what the last property is. Sometimes it's really easy and we can do it all in one shot when we've got really nice handy ratios or conversion factors. But in this case, I have to stop there and I have to use this equation because there isn't a handy factor that converts it, but I can use an equation that does that. Okay, and that's the end. Oh my goodness. Look at that. You can hardly read it. Can you read it in there? Yeah, it's kind of readable. Oh, it's on the sheet. Oh yeah, it's on your sheet. The homework, even out of the textbook, is on your sheet. No need to read it then.